let's go and apply the formula. What sort of things can we do? How will it make our life easier? Exponential functions. Now we said e to the iota theta was cos theta plus I sine theta. Basically I can replace the argument with whatever the power is. So if I made that power or argument iota theta plus multiples of 2 pi k, in other words we're going around the circle, I'll be in the same position and it'll give the same answer. So I could expand on that formula and make it cos of theta plus 2 pi k plus I sine of theta plus 2 pi k, which will give me the same answer as cos theta plus I sine theta, because we're just going around that circle completely. One revolution. We'll be in the same spot. And that will work as long as k is an integer. It has to be a multiple of 2 pi. A fraction of it, it won't work. And what that then means is, well hang on, these two things are actually the same. E to the iota theta plus any multiple of 2 pi will be the same as e to the iota theta. They actually are the same thing. It means it's a periodic function, just like the trig curves. It's a periodic, it's going to repeat every 2 pi I. And now we can use exponentials to solve trig problems, because we have this link now between exponentials and trig. Some of these identities that we've proven before, we can now convert this into another way. Remember this one? We said this is really handy when you've got a number plus its reciprocal or its conjugate, if we're talking about something with a modulus of 1. We said it was 2 cos n theta when we added them, 2i sine n theta when we subtracted them. Okay, if we rearrange this, we end up with this formula. The cosine of a multiple of theta will be a half of, we're going to add the conjugates together basically. So e to the, wow, the order I put the pronumerals in there is probably a bit strange, but I've gone n theta I and minus n theta I. But essentially we're saying the conjugates, we're going to add them. So cos n theta will be a half of that. And sine n theta will be when we subtract. Now, that will allow us to prove things. There it is, probably the first trig identity we ever see. Sine squared plus cos squared is 1. Well, if I now substitute in, n of course is just 1 in this case. If I substitute in for sine theta, so 1 on 2i, it'll be e to the iota theta minus e to the minus iota theta, and we're squaring that. And then add cos squared. If we expand the whole thing out, and we'll see there's some cancelling here that happens. I'm left with a quarter times 4, which is 1. So we've proven sine squared plus cos squared is 1. But using exponentials to do it. How about this interesting formula? Sine cubed theta is 3/4 sine theta minus 1/4 sine 3 theta. If I wanted to prove that. Well, sine cubed then, that's when we subtract the conjugates, that'll be over 2i. We're cubing that expression. Now when I cube it, that's what I get. I want to pull out the quarter so that I'm left with 2i on the bottom of the fraction. Because remember those two formulas I'm using, cos had 2 on the bottom, sine had 2i on the bottom. So I want to be left with that on the bottom. Now what happens to the top? I group the things that have the same coefficient. So 3 goes with the e to the iota theta minus e to the minus iota theta. You'll notice I've changed the sign because it was a negative 8i on the bottom, so I've applied that negative into the top of the fraction here. But have a look inside the parentheses. There's that pattern again. So the first one is the sine of theta and the second one is the sine of 3 theta, and there's a very quick way of proving that identity by making use of it being an exponential. How about this one? Product to sums. So the 2 sine alpha cos beta is sine alpha plus beta plus sine alpha minus beta. This one's a little bit more work, but this is what we're going to do. Okay, 2 times, there is our form for sine, so the difference, and times the one for cosine where we added the conjugates. Okay, if we expand this out, what we do, remember we add the powers, so I end up with, it's over 2i as the common denominator, e to the iota alpha plus beta plus e to the iota alpha minus beta minus and so on. Hang on, I'm going to split that into 2 fractions, conveniently. Fractions where the powers are actually the the same. Well, one's positive, one's negative, but I mean the first one has I times alpha plus beta in both of them, and the second one has I alpha minus beta in both of them. But hang on, that's in the form of sine. So the first one is sine alpha plus beta, and the second one is sine alpha minus beta. Again, a very quick way of proving that relationship. How about finding the roots of complex numbers? Yet another way of finding the square root of a number. 1 minus the square root of 3i, we're going to find the square root of that. So z squared is 1 minus root 3i. I'm now going to put it in exponential form. Now its modulus was 2, its argument was minus pi on 3. Well, that's z squared. So z will be the square root of 2 e to the, well, it'll now be minus I pi on 6. But remember, we said we could go plus 2 pi k. Well, I'm also dividing the power by 2, so now plus pi k. I need two answers, so I'll make k equals 0 and 1. And there's the two answers in exponential form. Want to get it back? All right, I can convert it back again. I don't actually have to write down the mod arg form. I could go straight to this because I know the modulus is root 2. I know the argument is minus pi on 6. And oh, well, for the first one it's minus pi on 6, the second one is 5 pi on 6. And so there we have our two square roots. HSC question from 2020. Question 9, you'll notice, it was actually a multiple choice question. But I'm not going to give you the multiple choice here, I'm just going to do the question. What is the maximum value of this expression? Absolute value of e to the iota theta minus 2 plus the absolute value e to the iota theta plus 2, where theta goes in between 0 and 2 pi. That was going once around the circle. Well, if I let z be e to the iota theta, so I'm going to look at the picture here to solve this problem. Now the modulus of z is 1. I know that. So I am talking about points that are on this unit circle. If I draw every single point such that the modulus of z equals 1, then I have got every possibility for this e to the iota theta there. So I'm talking about that. Now what do these expressions become? Well, the modulus of z minus 2 I know is the length of the vector that joins z to 2, head minus tail. Alright, I mean I've just randomly put z, actually it's not that random to be honest, I've deliberately put it there, but there is one possible place for z. I've joined it up to 2. Z plus 2, the modulus of that, would be the length of the vector joining that same z, because they're going to the same point, but now to negative 2. Look at these two vectors. What we're saying is, where do we place z on this circle? So the length of those two vectors, when we add them together, will be the biggest it could possibly be. And that's why I deliberately chose that point. It's got to be at 1, or at minus 1, of course. It could be down here as well. As soon as you start moving this point, one of the vectors is going to become smaller, one will become slightly larger, but the largest the sum of them would be is when the two vectors are the same length. So that's why it's at 1 or at minus 1. I can just do a bit of Pythagoras now to work out the length of that in that position. It's the square root of 5. So when I add them together, I'll get 2 root 5. That would be the maximum of those two. It was a really nice multiple choice question. It was multiple choice, so you did have options to choose from, which sort of helped you along the way. But it was really nice in that it tied in a lot of stuff there. We had to think about, locus, what does the picture look like? We had to use exponential form, so really nice question. The following year, you'll notice, by using part 1 or otherwise, in part 1 you had to prove this trig identity. So rather than prove that, I'll just say, well, all right, let's assume we've done that part. So by using part 1 or otherwise, we have to show that the real part of e to the iota pi on 10 is equal to the square root of 5 plus root 5 on 8. And by the way, you probably just heard me say iota instead of I, because that actually is what that symbol is. It's not actually I that we use for the imaginary part. It's actually the Greek letter iota. It looks exactly the same, of course. But that's what it is. All right, well, the real part of that we know will be the cosine of pi on 10. Because if we convert it back to mod arg or polar form, we'd get cos plus I sine. Cos would be the real part. So we essentially are asking, what is the cosine of pi on 10? So if I let theta in this expression, because it said using part I or otherwise. They're giving me a big hint. So all right, let's use it. Let's substitute it into that formula that we've just worked out in part I. Then 16 cos pi on 10 to the power of 5 minus 20, and so on, will equal cos 5 theta. Well, hang on. When I multiply pi on 10 by 5, I get pi on 2. And I know the cos of pi on 2, or 90 degrees, it's 0. I know all of that is equal to 0. I can create now a polynomial equation to solve. And that will get me a value for x, which is cos pi on 10, which is the real part of I pi on 10, which we have to show is the square root of 5 plus root 5 on 8. It all links back eventually. So, okay, let's solve this equation. First thing I did was divide everything by x. Now I know we always say you cannot divide by a pronumeral when you're dealing with an equation, which is correct, but there is one proviso. If you know that x cannot equal 0, then you can divide by it. Because the only thing you're not allowed to do is divide by 0. So normally we don't divide by x because if we don't know what it is. But in this case, I do know what it is. I've let x equal the cos of pi on 10. And the cos of pi on 10 is not 0. So I can divide by x in this case. That gives me a much nicer equation to solve. It's actually a quadratic when you look at it. I mean, it's a quartic. But I can treat it like a quadratic. Okay? Put it into the formula. X squared will be 20 plus or minus the square root of 320 over 32, which is, and look at that, that's what we're looking for, 5 plus or minus root 5 on 8. So x will be, which is the cos of pi on 10, the square root. Well, hang on, whoa. Shouldn't I have gone plus or minus? No. Because I know pi on 10 is an acute number and the cosine of pi on 10 must give me a positive answer. So I don't need to go plus or minus here. I know it has to be positive. But I've still got this plus or minus. Which one is it? I can't just go, oh, therefore, there's my answer. I need to justify why I picked the positive one. So it's either going to be 0.59 or 0.95, one of those two. Let's go to the cosine graph. There's the cosine graph. And if I just have a look at the y values of the cosine graph, there's pi on 10. Now I'm going to use pi on 4 as a reference point because I know that value is one of our exact values. It's 1 on root 2, which to 2 decimal places is 0.71. Now you look at my two possibilities, 0.59 or 0.95. One is less than one is less than 0.71, one is greater than 0.71. So if I look at my graph, I can see which one I need. So I want the bigger one, 0.71, which was 5 plus root 5 on 8. And so there we have shown cos of pi on 10 is the square root of 5 plus root 5 on 8. So there's some questions where we play around in exponential form as a way of solving it.